in that configuration. So either we stretch up a little bit this first joint and rotate 90 degrees, but we can also keep it low and rotate Q2 to a smaller angle. Now the question is, can we control? And when we put our 1 kilogram mass in both cases, and when you use the calculations in the torques, you will see that the forces and torques applied to different joints depend on the second and third coordinates. So in fact, depending on the configuration of the robot that you select, you will get different forces and torques of the that act on different joints. So knowing that, you can also think about the optimization of the force in different joints. And it is so-called null space motion because you keep the end effector in the same place, but you can move this joint up, rotating the others, and also changing the length of the third one. Keeping the effector in the same place from different locations, you can get different forces acting on the joints, and you can select the kind of the force that is the best in your situation. So for example, we know that the torque in here, when we have the long arm and the force is perpendicular, will be much stronger than here, because here we just have a small component that results from the sine of the angle between the arm and the gravity acting on the object. So that's what happens here. Null space optimization, that subject you need to remember that exists in redundant robots that you can also apply to force. Okay, so I will just call all the elements in here. So what we need to consider when we have the interaction control of the robot. So firstly, we need to consider the type, what kind of the dynamic interaction we have. So firstly, we may have kinematic constraints. So that's simply the obstacles that we can meet. So we can have a wall in front of us, or an object that we need to avoid, or we need, when we start interacting with it, we need to stop. Then we can have an inertial interaction. So because of the movement, especially rotary movement, there will apply certain forces that we will need to compensate. Then we can have a dissipative interaction. So when this force we are applying force that is dispersed by the objects, and we can have the elastic interaction where the force that we are applying is accumulated, and after releasing it will just create some extra additional movement. What we also need to consider is what we know about the models. So if we have a full knowledge about the models, if we have limited, or if we have the knowledge that is, let's say, the structure of the model is full, we know, and that's something that is that can be not seen as a full knowledge, but the parameters are unknown, and or they have some disturbances, so some random values that are that make it not correct. And as when I say about the model, is both the model of the manipulator that we work, and not only kinematics, we need also to know parameters of the dynamics, because forces are at the dynamic level. But the second side, we also need to know the model of the environment, both the geometry, so we need to know the shape of the objects, but we also need to know the mechanical features. Yes, so when we see a flat object and we are just approaching it, and we know and we want to predict of what will happen after a contact with the robot, we need to know if it's a concrete wall or it is, let's say, a sponge that will just will be not noticeable by the effector. So geometry, but also mechanical features, which means the elasticity and the reactions to the forces. And then the last part that we need to consider is our ability to measure the force. So if we want to control the force, we need to measure it somehow, and there are, well, three options. So either we can directly measure the force that is applied. So we have like a force sensor somewhere at the end of the end effector, and we just measure the force directly, and we know what happens. So, for example, in this UR3 robot in the laboratory, we have the force sensor that like 6 degree of freedom force sensor that is mounted just before the effector, just before the gripper, so we can measure the force quite precisely directly. But you can also measure the forces in an indirect way, and for that we can in fact use the formulas that we were showing in the statics or in the dynamics equation, because you can, when you already know the full model of the robot, you can say, okay, so then we have all these dynamic equations, and when we put these equations, as you remember, we get something like that. Dot Q, and we had that's the controls, which we can say that those are the torques that we apply to the robot. And it is in the situation when we don't have an object. But if we have, let's say, we add here some external force, we can transform this external force to the we can transform this external force to the joint space, and to compensate this external force, we need to add some additional torque to keep the manipulator in the stable position. So you can use that property for indirect force measurement. So when you know that when you have a, let's say, compensator of the movement, you keep the manipulator stable, someone adds some external force to it, and to keep it stable again, you need to apply increased torques to the robot. And when you measure this additional torques that you are adding, you can evaluate what force was applied. So it's like indirect measurements resulting from the stabilization, from the additional force torques in the motors that you needed to add. You just get the information, and transforming it to the external task space, you get the value of the force. Of course, indirect measurement is less precise than the direct measurement, but it is still possible, and it is used sometimes, for example, for safety for safety features that the robot notices when the force that it applies is bigger than it's expected, so it needs to switch off the movement because of the probably appearing some collision. Okay, so those are the two cases that that we really know what to do. There is a third case when we have no option to measure the force, because we cannot attach a force sensor and we cannot precisely measure the torques for some reasons. Yeah, and then we have no force measurement, and the things becomes more difficult on how to control the force without knowing what the force is. Okay, so taking all of that into account, we can just go further, and we can look on the different methods on how to do that. Just to see example of how this force sensor look like. So if someone wants to see that it is and that it exists, it's this module in the robot. How does it work? When you have the flange of the original manipulator, you have here a force sensors. They can have a different constructions, in fact. Okay, so that's our force sensor, and here we attach the gripper. So what happened? What may appear in this force sensor? They are force sensors that work on a mechanic way, pneumatic way. For example, the mechanic structure uses, well, as you probably remember, last lecture, we were saying about the parallel mechanism, like Delta or the Stewart-Goff platform. And in fact, they are, for example, the mechanical solutions for this force sensor, they use as something similar to the Stewart-Goff platforms. Working on a different, with, let's say, reversed principle, because Stewart-Goff platform, we control the movement of these legs to get a certain change and force. Here, there is a measurement of the forces in each direction that can be transferred to the measurement of the force that is applied at the end of the effector. So that's a similar looking structure, but on a reverse type of operation. Okay, so when we look at the types of the interaction control, we have the passive control and, of course, the active control. The passive control is when we don't put anything in the controller, and in fact it's a bit less interesting for the people from our faculty. So if it's not in the electronics, if it's not in the controller part, well, it's not something that we do, because this passive control is usually the result of the mechanical design. But let's say about it, just to know about the properties that it has. So it uses some structural compliance of links. So recalling the video from the beginning of the gripper, yes. So it has a special shape that when you apply the force, the shape of the elements changes, and the force is automatically regulated by the mechanical structure itself. So passive control, we associate it with the mechanical design, elasticity, and springs that we use. What is good in this method? It is simple and cheap. Yes, so when we already have it, we don't need a force sensor to measure the force. We don't need to change anything in the program, in the controller. We don't need to react to the force. Everything goes automatically with the mechanical design. That's why it is cheap and simple in the sense that we don't need to do anything more with it when it already exists. It usually, because we don't need to make any calculations and we don't use active actuators, it usually also has the faster response than the active systems. So it does. The normal control system requires this control loop that we have the measurement, we have processing of the data, and sending the output to the actuators before the reaction appears. So here, this automatic reaction is usually faster. The problem with this is that it needs to be it is very specialized. So if you change, let's say, you decide that you want to grasp a different type of the object, a different shape, a different size, then you need to redesign it again. So you need to work again and have a completely new solution. So it's not universal, and that's why it has no flexibility. Okay, so when we say about the active control, when we have the active control, this compliance and reaction to the forces is ensured by the control system. So the controller gets the information about the forces, applies certain modifications to the output, and that what the actuators are responsible to creating the proper reaction. More expensive because it requires measurement of the force, and yeah, that's slower, as we said, requires this full control. The advantage, it is flexible. Yeah, so we can have, like in UR3, we have a gripper that can grasp any, wider range of the objects that we have with different masses, and we can still apply the same algorithm that will not be dependent on the shape or the size and the weight of the object. Okay, so passive control and active control, it's always depends on the applications of which one you would prefer to use, but we will tell a little bit more about the active control because of the field where we are. So we are interested in the control systems. So that's we will focus on these active control types. And so when we have the active control types, we can talk about the either impedance or admittance method, which are methods for indirect force control, or we can say about the hybrid force motion control, which is a direct force control, but it is also can be combined that we will have a partially position controlled robot and partially force controlled robot. Okay, so how the impedance control works. Of course, we will talk here about the very simplified models. So just to make a small disclaimer that if you want to apply it in practice, you would need to go a bit deeper into the formulas, and it's not directly applicable in that form that we will have here. It's just supposed to give you the idea of how it works and what is the purpose of that method. So we start with the dynamic model, and in the dynamic model, as you can see, we have our original torques, and we have these torques that result from the static formula. And when we use the so-called computed torque control, we use this formula for the second order error equations. I hope you remember that we are also calculating this computed torque control on the introduction to robotics. Out of these parameters, we have this KD parameter, which is working on the derivative level, on the velocity, or the derivative of the error, which, let's say, we call the velocity of the error, and KP, which works on the error itself, on the value of the error. And we can, when we look at the analogy of the physics of the spring damper model, we can see these parameters KD as damping and KP as stiffness of the control system. Okay, and what does the impedance control do, in fact, is that it virtually adds some corrections to the path, depending on how deeply in the object virtually a path in the object is. So let's say we want to follow a path next to the object. So we have an object, we want to go along this object very closely to that object. For example, because we are doing like welding of the on the object surface. So we have our welding head directed in here. We have a gripper, and we just want to go down along the objects and just make the operations step to step, just following the surface. And normally, if we apply the regular controller, like a computed torque PID controller, it would mean that depending on the error, we will get a corrections to the movement that will be, if we shift, okay, that will usually work in that way, that it will be like symmetrical. So if we go certain value of the distance to the left, we get additional corrections that will just that will be shifting our end effector towards the path. And if we go in this direction, we get a symmetrical, the same shift that says, okay, so we need to go to the path from that way. But it is like a symmetry on both sides. This, let's say, force, well, the part of the controller that is making the correction is the same on both sides, on the, let's say, free space side and the object sides. Instead, when we add the impedance control, we will be saying that, okay, we don't want it to be symmetrical. We want this force go very deeply in here because we have a stiff object. So if we are just approaching too close to it, we just need to make a very quick correction to move back to simulate how this object is stiff, and we cannot really go inside that object. So it is just making a corrections to that idea, adding some non-symmetrical corrections to the error between the real path that the robot follows and the planned path of that robot. And of course, if we have the robot that is not completely stiff, so it can be bending a little bit, this method works quite well, because we indeed can get inside the object a bit, and then the method can really effectively apply these corrections. When we have the object that is, let's say, fully stiff, like this concrete element or the steel plate, then this method will be less effective, because we cannot really make any error toward the object that could be corrected. Okay, so what we how the scheme works: we have this manipulator with the inverse dynamics. We calculate the direct kinematics, and we have these corrections that adds just a coefficient resulting from the shifting from the path towards the object with the virtual stiffness of the objects, and that makes an additional corrections to the movement of the robot, and these corrections will be pushing away the end effector from the object. So that's one of the idea, not really measuring real force, and just simulating it in with the virtual movement. More interesting idea is the hybrid force and motion control that finds many applications in practical works, especially in assembly. And this approach works in that way that it divides all the possible directions of movement. So if we say about the 3D space, we have like 6 directions, 3 linear and 3 angular, and we divide it into 2 parts: the part that is force controlled and part that is only position or velocity control. So in one we can have certain direction when we can work with the movement and we want to freely move, and the second direction that we want to control the force. When you imagine, for example, a polishing task, so we have the object and we have a head that is making the polishing, and we know that we need to apply a certain force to that surface here, and we need to control the force in this direction. So when we have the coordinate system, as we work like that, so this direction will be force controlled. But on the other hand, going along the object, we just change the position, and we are not interested in the force that is applied. The force can be any. So we have the position control in the other direction. So here we just touch the surface of the objects. So we have a fixed position in X. Let's say it's X and Y. Fixed position in X, but we need to apply certain force to it. So we have this force control, and here we have the force is not interesting. We are changing the position. We have the position control in Y. So that's how this hybrid force motion. Those are the assumptions for the force motion control, the hybrid version, that we select of which directions are force controlled and which are the velocity controls. And generally, all the space that we have is divided into these two modes, and they are just treated separately. So, okay. And then we get this hybrid controls scheme. And as you can see, this is the standard view. Of course, it is again a bit simplified scheme. It's working in the place where we already are in the situations of the of touching the object. That I will comment on later. So when we look at it, we have in fact two different controllers, and this motion controller we have at the bottom and the force control that we have at the top. They just generate the vectors in the orthogonal directions to each other. So in that sense, they do not disturb the other type of the control. So all the controller that we have here, especially you could see this SF here and SV is like a selector matrix. So it selects from the controller the directions in which we want to act. So let's say the motion controller gives us the vector of x, fx, fy, fz, and we say, but we wanted on the example here, we wanted a position control on the y. So we use the selector matrix that says, okay, we keep this 0, 1, 0 here, but we remove the two others coordinates. So that's our selector matrix for the velocity control. So we get a vector which will be like that. So we just remove the directions that we don't want to control in a position. And the same analogous things we do here with the SF, which is like a complementary matrix that selects the directions which are supposed to be force control. So again, the idea is simple. We take the usual force controllers and motion controllers, they calculate the solutions by themselves separately as the usual, as if we controlled fully in force or fully in motion. But later, from the vectors, we just select proper directions and combine directions from the two controllers into one controller of the system. And when we look at the examples, how this will look, those are taken from Handbook of Robotics. So you have, for example, this insertion task. So when we have this insertion, you can see that when we have the x, y, z, and we have rotation in x, rotation in y, and rotation in z. So you can see that the free motion that we have in this case is that we can move the robot, move the one objects and the effector in the z-axis, and we can also rotate around the z-axis. Those are free movement that we have, and all the other movement from the 6 are the force control. So we need to control the force in this direction, and we also cannot really rotate either in this or this direction. We cannot rotate this object. We also need to control this rotation forces as well, rotation torques. Another example is for crank turning. Then again, you can see that locally we have the velocity control in this direction, and we have also the rotation in Z, which is just not the best shown here. So we have, those are three movements in the those are allowed directions of the movement, and we cannot move it either in this direction, we cannot move it down, we cannot rotate it in that direction, we cannot we cannot rotate it in so XZ, we cannot rotate it in X, and we cannot rotate it in Y, which is we cannot rotate it in that way. So all these four green arrows indicate the force and torques controlled directions. Okay. And okay, and the remark I was to say is while the force control or motion control itself are just quite clear, and this hybrid control works also well according to the scheme that you have, the usual problem is switching between the two different controllers when you are approaching the object. So you have situations when you are away from the objects, you are moving in a free space, so you are using just a position controller all the time, and suddenly you are getting into the contact of the with the object, and then you switch to the, let's say, impedance controller or hybrid force position controller, and you switch to another value. The problem that can appear is that when you switch to another controller and the controls that are generated by the, let's say, free space controller and the in contact controller, and the forces are not continuous, it may happen that you get into a chattering situation. So so when you are approaching here in the free space, the controller generates, okay, saying, okay, we have a big force like that. And when you are coming to the contact, in the contact phase, so you got to the contact point, then the controller starts to generate the force in the opposite directions to avoid this applying too much force to the object. So what happens is that your position, when you are just going, and when this value, so when you have this, let's say, the error and the force, and they are not continuous, so we have, okay, we have an error and we have a certain value of the force here, and then we have the certain force here. It means that we are approaching and we have certain velocity, and when we get into the touching the object, we switch to another controller that generates a high force in the opposite direction, and we are immediately shifted away, and then we switch back to the free space controller, and so on. So that's the situation. Passing from one controller to another is a part of the difficult that needs to be usually worked out well using either a method that will ensure that the switching between the forces is smooth here, or that we have a certain area of the intermediate reactions, or calculating the approach itself. There's also an attitude that is sometimes used, that you have a third, in fact, the third controller that is like an intermediate that just responsible to control in the phase of passing from the free space control to the contact point. Just to avoid these chattering situations and some unpredictable or not wanted kind of the movement at the contact point. Okay. So what we have more. We have okay. So some of the methods that we are talking, the simplifications. I said that the equations and the controllers are simplified. They are simplified in the sense that they assume that we know the parameters of the environment. So we know how elastic is the object that we are touching. We know where exactly this object is, and so on. Then you can put everything into the equations, and yeah, and it will work well. The problem in the real world is that, of course, the equations are true, but you don't know the exact parameters, and quite often also the parameters change, and you can have the same objects in one point, and a different point can have a slightly different elasticity, and the behavior will change. So that's something that in real cases we don't have the parameters of the environment, so we cannot rely our algorithms on it. So we need to add certain robustness or approximations and so on, and that's the element when this simplified algorithms become more complex. Unstable transition between contact and non-contact motion with stiff objects. That's what we were talking about. This chattering case that may appear that we may want to avoid. And finally, we have the Pine-Lev paradox of the friction that is caused by the friction between the end effector of the object. Yes, when you are moving well next to each other, and we are usually drawing in a mathematical way, so we have lines that are completely straight, and that everything is ideally flat and so on. In fact, when you are moving along the objects with the end effector, the surface is at the microscopic level, it is rough. So these forces, they are just changing in every point. They will appear certain vibrations. These vibrations can be measured as forces by the sensors, and because the sensor will measure certain forces, the controller will try to react to these forces, change the movement, and so on. So that's moving in contact with objects. That's why it becomes more difficult, and that's something that also needs to be considered into the practical applications. Okay, and just to summarize of what will be important to remember is we have these three methods: the position, velocity, and force control. On the past lectures, we were focusing on the position and velocity control, but it is worthy to know that this force control is as third options. What it really is, what are the applications of this force control when we have to use it, and when it is good to use it. Yes, because in certain applications we have no choice and we need to use force control. In some applications we can use position-based control or velocity-based control, but using force control will give us some additional better performance of the manipulator. So what are the possible applications? And finally, what are the main approaches in these force controls? Okay, that will be all for the today lectures. Maybe there are any questions to the lecture itself. Okay, if there are no more questions about the lecture, the one organizational thing, the next week lecture, I would like to make some kind of a recap of the lecture and a summary of what was done, but also it will be a time to, if you have any questions that you would like to ask before the exam, if you have any doubts, something will need explanation, please prepare it. So we'll make split the next the meeting on the next Thursday on, let's say, my summary, and then the questions from your side to clarify certain doubts when they, if they appear. Okay, so
I have maybe one question regarding the project. If someone was already presented last week, do we have to appear today, or it's not necessary?
When you already presented, it's not necessary to be on a project. Oh, you say about project or seminar?
A project.
Okay, so no, for project, if you have presented all the 3 milestones, that's fine. So that's the only thing that is left then is the report from the project at the end, right?
Yes. Okay, thank you.
So just to be clear, if you have presented all the milestones that were expected and the working projects, yeah, that's you do not need to come, but remember about the report, the final report. Okay, if you have no more questions, then thank you for today, and we will finish now. Goodbye.
Thank you. Goodbye.
Goodbye.